Okay, so let's start with a 5-minute recap. So we have been discussing that a programmer or any programmer, when we write programs or any software even, they have these kind of expectations from the memory. And so memory address will start from 0, memory will be contiguous, and there is this dynamic increase portion. So these three, so we initially discussed contiguous memory allocation, but that made dynamically increasing the memory really difficult. Also, memory was not utilized that well because of fragmentation. So then we moved to paging. And with paging, we found that the first three requirements are well satisfied. So the programmer gets a contiguous view of the memory, that the programmer can think that the memory is a contiguous block starting from 0. But physically, the memory, the device divided into pages, and the pages can be stored in non-contiguous frames in the main memory. This way, dynamic increase of the memory is also possible. So you can just, the OS can just allocate a new frame to the process if the process wants more memory. So now that the first three requirements are satisfied, we go towards the fourth requirement, which is as time passes by, processors require more and more memory. So at one point of time, maybe processors were happy with only a few MBs of memory. Now, with more and more complex programs being written and new kinds of technologies coming in, nowadays programs require huge amounts of memory, and often like 32-bit address space. That means 2 to the power 32 bytes of memory is required. Often even more, like 64-bit virtual address space. That means 2 to the power 64 bytes of memory is required. Right. So as time progresses, programs want more and more memory. So that is the requirement which we now need to fulfill. So, the issue with more memory is that, fine. So one thing is definitely more memory is required. The other thing also to worry about is that page tables are getting larger. Right? So maybe in very old days, there were small page tables. But nowadays, page tables are getting larger because every page has to be tracked. So a few bytes are needed to keep the information of every page in the page table. So as the programs are expecting or demanding more memory, more entries need to be kept in the page table, and page tables are becoming huge. Right? So the main challenge is to dealing with large page tables efficiently. That is what we are discussing now. So we understood that, first of all, page tables need to be in the memory itself. Okay, so somewhere the page table also needs to be stored. That will be stored in the memory itself. But that immediately creates two problems. One is that now it seems for every data access or instruction access, 2 memory accesses will be required. One to the page table to get the frame number of the data, and next to the data. This is bad because memory access is low. So we would not like to spend 2 memory accesses for each data access or instruction access. But this problem has a simple solution called TL. So we basically use caching. So a part of the page table is cached in a special cache memory known as TLB, Translation Look Aside Buffer. This is what we discussed. So this is very much similar to caching. So I think it's understandable. So the page number which the CPU generates is first matched with the entries in the TLB. And intuitively, the TLB stores the most recently accessed or most frequently accessed pages and their frames. So if there is a TLB hit, then the frame number can be immediately obtained from the TLB, and we do not need to access the memory for the page table. We can directly get the frame number of the data which we want to access, which the program wants to access, and then we can directly access the memory. If there is a TLB miss, then we need 2 memory accesses. First to the page table to understand which frame the data is in, and then to that frame to get the actual data. And of course, in this case, we will update the TLB also, because we know about these principles like locality of reference and temporal locality. So if a page has been accessed, most likely it will be accessed again soon. So yeah, I mean, it makes sense to bring that entry to the TLB. Okay, so this is the first problem about taking pages to the page tables to the memory. That is, access might become slow, but using TLB, we have seen how we can reduce that slowness. So we did a small numerical and we found that so nowadays caching is quite advanced. So it is quite normal to have 99% hit rates. So if the TLB has a 99% hit rate, then I mean the effective access time is almost as good as just accessing memory once. Okay. So this problem is kind of relatively easy to solve using a TLB. But there is another big problem with taking page tables to memory. The problem is this, that page tables have become huge. So we just understood with this small numerical yesterday that it is quite possible that page tables have 1 million entries. Right, so you can see the numbers here. So 32. The main problem is happening because programs are demanding more and more memory. So nowadays, programmers want 32-bit logical address space or even 64-bit logical address space. So they want huge memories. Like and I mean, don't think that these are like some very complex sure, programs are complex possibly, but don't think these are some programs which only some people write. Like even when we do our research nowadays on big data, we have to deal with lots of data. And so it is quite natural for processors to want several GBs of memory. Okay. So in those cases, if you see the numbers here, it can well happen that the page table has 1 million entries. And the size of the page table becomes equal to 10 pages. So now we have a problem. We came to paging because we wanted to avoid contiguous memory allocation. But now we have a situation where page tables have become so large that they would require 10 pages or more of contiguous memory. Right? So that is the problem that we now will discuss how to solve that. So there are 3 in general solutions for this problem. Let us understand. Okay, I must say that the next few slides might be a bit difficult to understand, so pay attention. If you have any questions, ask. In general, like the slides will be available to you. You will see the books. I mean, we expect you will see the book. So therefore, even if you don't understand everything, bear with me and go through the slides, go through the book after this. You should be able to understand. So, but in the next few slides, pay attention and ask if you have any questions. So let us start with the first solution, hierarchical page tables. So the problem is the page tables have become too large and we do not want to allocate so much memory contiguously for storing page tables. So in this method of hierarchical page tables, we break up the logical address space into multiple page tables. Okay, and we have a multi-level page table also. So essentially, this is called paging the page table. The term used is POPT, pages of page tables. Okay. So let's understand what is happening. Remember, page table is also stored in memory, and it will be also divided into pages, just like other data. So this is how the picture looks. Looks complicated, but just let's understand. So till now, we were only talking about a single page table. We were assuming that the page table at least is contiguous, but now it's not so. So this is the page table, which is shown in the middle. And you see, now the page table has multiple pages. Okay, this is what we were discussing, that a page table can have 10 pages. So now the page table will not be contiguous. These 10 pages, let's say the page table contains 10 pages, these will actually be stored non-contiguously. Okay. By the way, one thing, let me clarify. This picture shows that this way just to, just for visualization. Understand that all these pages of the page table, they are actually stored in the memory itself. Right? So do not think that the page table occupies some other storage area other than the memory. No, actually what is shown here, this middle portion, this is actually part of the memory. Okay, this is just shown here for easy visualization. This is shown separately. Okay, so now the idea is that the page table is itself divided into pages. So this is first page of the page table. This is second page of the page table. And maybe this is the 10th page of the page table. Okay. And what is there in this page table? Pages of the page tables? Simple. What we have understood till now. So basically it contains the frame number. Okay. Now the thing is, now these 10 pages of the page table, let us assume there are 10 pages. These 10 pages of the page tables are also stored somewhere in non-contiguous memory. They are just basically stored as 10 pages somewhere in the memory. So we add an outer page table. This is contiguous. This outer page table is contiguous. And this stores the starting address of each page of the page table. Okay, let me repeat. This outer page table is contiguous, and each entry here stores the starting address of each page of the page table. So this entry stores the starting address of the first page of the page table, main page table. This entry here of the outer page table, the second entry, stores the starting address of the second page of the main page table, and so on. Okay. And in this scheme, how is an address translated? Let's see. So let's assume we have this two-level page table, an outer page table and the main page table. So a logical address, let's say we are dealing with 32-bit logical addresses and 1K page size. So a logical address is divided into two parts. This is what we have discussed already, a page number and a page offset. So because the page size is 1K, the page offset is 10 bits. And the rest 22 bits is the page number. But now, since we are using, so this was our scheme earlier, right? So there was a 10, let's say a 10-bit offset, and the 22 bits would be the page number. But now there is a difference. We are paging the page table. That means we have now two levels of page tables. So now this 22-bit page number will be further divided into a 12-bit page number and a 10-bit page offset. It looks like this. Essentially, P1, P2, and D, let's say. P1 is an index into the outer page table. And P2 is the displacement within the page of the inner page table. Right? So let's see what's going on. This is what is going on. So remember the picture 2 slides back. Now we have two page tables. The actual page table is in the middle. This is a particular page in the page table. And we have an outer page table. And the logical address now is divided into three parts, P1, P2, and D. P1 is an index into the outer page table. Okay. From this outer page table, we will get the starting address of a particular page of the page table. Okay. From this entry of the outer page table, which is indexed by P1, we will get the starting address of a page of the main page table. Right? And this P2 is actually a displacement within this page of the page table. So from here in this entry, we will get the frame number, actual frame number for the data, the starting address of that page, which contains the actual data. This. And then D will be used as an offset within this page. So essentially, D is an offset within for the actual data item within that page which stores the data. And P2, you might think, is a offset within the page of the page table. Okay. Let me proceed a few slides more, then I'll ask for questions. Of course, you see that now there is a cost, increased cost. So now it seems that for every data access, we require 3 memory accesses. First to the outer page table, next to the page, a particular page of the page table, and then to the data. Now, Let's give an example. Let's give you an illustration of how the page translation happens. After that, I can take questions. So suppose this is the scheme. We have this logical address. We have a two level page table, a main page table and an outer page table. Okay. And the main page table is divided into pages. So we have pages of the main page table and we have an outer page table which is contiguous. And we have this three-part logical address, P1, P2, and D. Okay. D is simple. D is the offset within the data page. So that we directly use. Right. Yeah. Now what we do? This first entry, remember, this is an index into the outer page table, or sometimes called the root page table. Okay. So we know that, there is a register which is storing, remember the root page table is also in memory. There is a register called root page table pointer, which is storing the starting address of the root page table. With that, we add this number 10. We multiply it by k, where k is the, what is k here? Any idea? What is k? Anyone? What is k? Exactly what Ravi says. K is the size of an entry in the outer page table. Good. Yeah, what Simant also said, this is the size of each entry. Right? So this 10 is the, so basically the program wants to access the 10th entry of the root page table. So 10 into k, we have to get the byte number, right? So 10 into k. So every entry is k bytes. So the 10th entry would be k into 10 bytes away from the starting address. So this 10 is used to access the root page table. So what does the root page table entry give us? It gives us the starting address of a particular page of the main page table. Okay. I repeat, this entry of the root page table gives us the starting address of a page of the main page table. That starting address is added with this 10, again multiplied by k, right? So see this this root page table entry, this gives us the starting address of a page table. Okay, that is added with this second entry, this 10, again multiplied by k, to get a particular entry in the inner page table. So remember, this is a page in the page table, a page of the main page table or inner page table. Within this page, the starting address of the page was obtained from the root page table entry. And within this page, we got to a particular data item by using this 10. Okay. And what does this entry give us? What do you think? The inner page table. What does this give us? What will this entry give us? Yes, good, what Srijan said. This entry will actually give us the frame number where the data is stored. Okay. So we will just get the frame number from here. And finally, we will use this third component of the address, this 12, as the displacement within this frame or within this page where the data is stored. Right, so there is a symmetry here. For each of these pages, see, we are accessing 3 pages, you might think. The root page table, the inner page table, and the data page. For each of these, we need 2 things. One is the starting address, the other is the offset within the page. So in case of the root page table, the starting address is in a register called root page table pointer. And the offset is the first part of the address. So we multiply that by k and we get it. A particular entry of that root page table. Now that root page table entry gives us the starting address of the next page that we need to access. This is a page of the inner page table. And we use the second part of the address here is 10 as an offset into that page of the inner page table. Now that entry of the inner page table gives us the starting address of that page or frame where the data is located. And then we will use the third part of this logical address as an offset into that page. Okay. So this is the scheme of hierarchical page tables. Now, if you have any questions, tell me. So let me just go back to that picture once. Yes, so this is the type of page table we are talking about. The inner page table or the main page table is now split into different pages. And these pages may actually be non-contiguously located. Okay. Now we have an outer page table which is contiguous, and each entry of this outer page table gives the starting address of a page of the inner page table. Okay. And correspondingly, we have three parts of the logical address now. We have three parts of the logical address. And each part is used to, somehow we have to know the starting address of this page. So in case of the outer page table, the starting address is stored in a register or page table base register. And after that, from each entry, we get the starting address of the next page to access. And then the next parts of the logical address are used as offsets into those pages. Okay. Yeah, so if you have any questions with this scheme, now tell me. Okay, great. So no questions. Yeah, so this is the final way in which your address will be translated. So each part of the address is used to access one level of the page table. And the final part is the offset, which will be used to get the data actually. Right, so essentially just remember that each entry of the outer page table is storing the starting address of a page of the main page table. Okay. Fine. So till now, all of our discussion was about a 32-bit logical address space. So this kind of worked. Okay, fine. Soon programmers started demanding more memory. Right. So now many programs require a 64-bit logical address space. Wow. Now, if we go to a 64-bit logical address space, even a two-level paging scheme is not sufficient. So let's say the page size is 4 KB. Then the page table has 2 to the power 52 entries. It's a huge, huge number. So in a two-level scheme, the inner or second level page tables could be 2 to the power 10 4-byte entries. Okay, remember, the page size is 4 KB, so 2 to the power 12. Now let's say each entry of the page table is 4 bytes. So how many maximum page table entries can you store in one page? Remember, the page table will also be stored in pages, right? The pages of page table, POPT. So if one page table entry is 4 bytes long, how many entries can you store in a page of 2 to the power 12 size? Clearly 2 to the power 10, right? So you see the in the so if you think of the logical address space, which is now 64 bits, this D is within the data, within the data page, so it's 12 bits. For the inner page table, we know that there are 2 to the power 10 entries. So we might keep 10 bits for accessing the page of the inner page table. Because we know there are 2 to the power 10 entries in the page of a page table. So we might keep 10 bytes here, 10 bits here to access those, to access a particular entry within a page of a page table. But even that leaves out 42 bits. So the outer page table, remember the outer page table, we assumed it is contiguous. But now the outer page table will have 2 to the power 42 entries. That means almost 2 to the power 14 GB. So clearly we cannot have this contiguous. Okay. So what to do? Any suggestions? Yes, basically what Deep said, go and add more levels. So instead of having a 2-level page table, think of having a 3-level page tables. So yeah, so add a second outer level page table. So instead of having 12, 10, and 42, so clearly 42 entries, we cannot allocate contiguous memory for 42 page table entries. Sorry, 2 to the power 42 page table entries. Right. So if the outer page table would have 2 to the power 42 page table entries, we cannot allocate contiguous memory for that. So add a second level of outer page table. Right. So now we have 3 levels of page tables. So inner page is 10, even outer page is 10, and second outer page is 32. But even in this example, the second outer page table is still 2 to the power 34 bytes in size. So 2 to the power 32 entries, each of 4 bytes. So 2 to the power 34 bytes in size, which is 16 GB. We cannot even allocate 16 GB contiguously. Also, we can add more and more levels, but then there's a big cost. So now 4 memory accesses are needed to get to one physical memory location. Now you have 3 levels of page tables, right? So you first access the first level page table. That gives you address to a page of the second level page table. You access that. That gives you a address of a page of the first level page table. You access that, and then you get to the data. Then you get the address of the data. So for each memory access, now we are requiring 4 memory accesses, 3 to the page tables and 1 to the data. Clearly, this is not feasible, right? So this hierarchical page tables, they used to be popular. They are still used. They are still used in slightly smaller systems. But if the systems are actually giving such huge memory spaces, like 2 to the power 64, they are actually giving such huge logical address spaces, then this hierarchical page table is not sufficient. We'll have to go to other alternative mechanisms. Okay. Now the alternative mechanisms are simpler. We will study them. But before that, this was the most complex part, I think. So any questions here about this hierarchical page table? So if you have understood the 2-level page table, the 3-level, 4-level page tables, if they are used, should not be too much of a problem. Exactly the same sequence of steps goes on. So you access up one page table, that gives you the starting address of a page of the inner level page table. Then you access the inner page table. Again, you get a starting address of a page of the even inner page table, and so on. But as we understood that with really large logical address spaces like 2 to the power 64, this is also not enough. Like you just cannot go on adding multi-level page tables and increasing the levels because it is coming at a big cost. So for each data access now you require 4 memory accesses. That is practically not feasible. Okay. So this kind of hierarchical page tables are still used, but if in systems where there are in systems which allow really large logical address space, some other mechanisms have also started to be used. That is what we are going to discuss, and they will be simpler. Let's discuss the next scheme, hashed page table. Okay, so you all know hash tables. So in hashed page table, I mean, this is commonly used in those systems which allow more than 32 bits of address space. Like systems nowadays, some systems are there which allow 64-bit logical address space. So in those kind of systems, hashed page tables are sometimes used. And what is the idea here? It's simple, much simpler. Virtual page number is hashed into a page table. And each page table entry can contain multiple frame numbers, let's say. Basically, a chain of elements. So just like we do in hashing. So in hashing, if multiple elements map to the same hash table entry, one solution is to just add a linked list with all those elements. That is what is exactly done. Okay. So the picture is something like this. So now we have a hash table. This page table is now a hash table. And each entry stores multiple frames. I mean, addresses of multiple frames. Of course, we need somehow to distinguish between these. So now each entry stores a new field also. So each element stores these. The virtual page number, which is generated by the CPU actually, the value of the mapped physical page frame, and a pointer to the next element. This is for the linked list part. Okay. So essentially, remember, okay, so let me ask a question. This is the new part. Why did we not have to store this in the page tables that we discussed till now? So the physical page frame we always needed to store. That was the idea. The page table entry will store the physical page frame number, physical frame number. But this is the new thing, the virtual page number. Why did we not need to store this earlier, and why are we having to store it now? Any answers? Okay. Okay, Ravi, can you unmute and say like, yes, you are right. So previously each page table entry directly gave us the frame number. So what was the virtual page number? Did we not need the virtual page number at all? Can you unmute and say?
Sir, the virtual page number means the page, like the page number in the page, the entry number in the page table itself.
Exactly. So until now, page tables were like an array. So the index into the array is the virtual page number. So if the virtual page number was 0, that is the 0th entry of that page table. Virtual page number 1, that is the 1th entry of the page table. So I think Deep also meant the same thing. So essentially, page tables till now were at a kind of arrays. So the index was the virtual page number. For virtual page number I, that entry was found in the ith entry of that page table or page of the page table. But now we are talking about storing multiple, storing entries related to what multiple virtual page numbers in the same page table entry. And that is why we need first of all, we need a linked list kind of thing, because we need to store here multiple entries. And we also need to explicitly store this virtual page number to distinguish between which entry in this linked list are we matching with. Okay. So essentially here, logical address is a page number and a offset as usual. This page number is hashed, and that leads us to an entry of this page table, which is now a hash table. Here we will have multiple entries. We may have multiple entries connected in a linked list. So which entry should we match with? For that we will use this number P. See, P, Q all have hashed to this same page table entry. But exactly which entry to use? For that we will use this P. So see, this entry matched because the virtual page number was P. So we will get the frame number directly from here, and we will then use it to access the physical memory. Okay, so this is simpler. As in, we do not need multiple levels of page table and all those stuff. This is just a page table implemented as a hash table. Only thing is, yeah, you need to store a linked list for every element, and you need to, because there are multiple, frames mapped to the same hash table entry, you need to store the virtual page number in order to match with the logical address. Okay, so this is much simpler. Fine. So any questions here? Okay. So that is one scheme which is commonly used nowadays with really large. So let me say multi-level page tables, it is not that they are not at all used. They are used in smaller systems, but if you really go to beyond 32-bit logical address space, which nowadays machines are giving, then multi-level page tables or hierarchical page tables become a bit problematic because of the things we discussed. Like you need too many memory accesses to go to a particular data. Of course, you can still use the TLB and all. But the thing is, if there is a TLB miss, then there is a huge cost. As in, maybe 4 memory accesses are required to access our data. So that is what people are not liking. So for really large logical address space, say 64-bit logical address space, people have started moving to hashed page tables. Also, there is another scheme which is not so popular, but just for the sake of completeness, let's just tell that. That's called an inverted page table. So this idea is kind of interesting, but it has a drawback also. That is why it has not become so popular. But till now, whatever we have discussed, we have assumed that each process has a page table that keeps track of all logical pages of this process. Okay, till now we have a page table for every process. But can we think differently? Say, the number of frames in the physical memory is fixed. So why can't we have simply a table which tracks which process is storing a page at which frame? That means instead of tracking for every process, instead of having a table for every process as to where the pages of this process are, why not track the physical memory frames? They are fixed in number, they don't change. So why not track the physical memory frames? So rather than each process having a page table, we now say we have a single table, inverted page table, where there is one entry for each real page, that means frame of the memory. So the entry will be the virtual address of the page stored in that real memory, plus some process ID or some kind of information, which will indicate which process is storing that page. Okay, so now we are completely inverting the situation. That is why it's called inverted page table. Till now we were saying that, okay, from logical address space, we will go to physical address space, and each process has its own page table and so on. Now we are kind of inverting the situation. And we are telling that we will store just one page table, system-wide. System-wide, there will be just one table, which will be called an inverted page table. And it will have one entry for every frame in the memory, right? And the entry will be the virtual address of the page. So till now, see, in the page tables, we always stored physical addresses, actual frame numbers, starting address of frames. But now we will store the virtual address, right? So the entry will contain the virtual address of the page stored in that real memory location, plus the information of the process that owns that page. See, only virtual address is not sufficient. I hope you understand. Because remember, every process assumes the virtual address to start from 0. So let's say the virtual address 100 does not actually mean, I mean, if you store the virtual address 100, that may mean many processes. Like every running process will have a virtual address 100 possibly. So just storing the virtual address is not enough. You need to store virtual address and information of the process that owns the page. Okay. So yeah. So this is now the kind of scheme. So now this page table is the inverted page table. Okay. The CPU generates an address which has both the process ID of the process which is running, which is generating this address, and then the logical address, I mean P, page number, and D. So now this inverted page table has to be searched for this entry, PID and P. Okay. See, only P is not sufficient. That is what I was telling. Only logical address is not sufficient because logical address for every process starts with 0. And so maybe 100, logical address 100, every process can generate logical address 100. So just not that, you have to match the PID also. Okay. And suppose you search with this PID P tuple in this inverted page table, and it matches with the ith entry. What does that immediately mean? This page is located in the ith frame of the physical memory. So then you will use the frame number I and the offset D to access the physical memory. Right? Remember, this inverted page table has one entry for every frame in the physical memory. So if the logical address generated has matched the ith frame, if the logical address generated has matched with the ith entry of the inverted page table, that means that this page is to be found in the ith frame. Okay. So this scheme definitely decreases the memory needed to store each page table, because now there is just one page table. Okay. Huge reduction in the memory. However, the cost is that it increases the time needed to search the table for a page reference. Right, and that is because searching, so see, your search key is the virtual address, like PIDP. But this inverted page table is not sorted according to PIDP. It is sorted according to this physical addresses as being the ith frame, the first frame is the first entry corresponds to the first frame in the physical memory. Second entry corresponds to the second frame of the physical memory, and so on. So essentially, the search key, I mean, just from algorithms, we know it is advantageous to search if the table which is to be searched is sorted according to your primary key. But here that is not possible. The primary key is the logical address, not the primary key, sorry, the search key. The search key is the logical address, and the table which needs to be searched, that is sorted differently. Right? So essentially, you have to do a linear search kind of thing. So that makes it a bit problematic, right? So people have thought of ways, but then yes, inverted page tables have not become so popular as, say, hashed page tables or multi-level page tables. So nowadays, like in general, okay, I cannot say for specific operating systems might be using inverted page tables, that I don't know. But in general, hierarchical page tables are used for smaller systems, as in systems which, say, give up to 2 to the power 32 memory for a process, that means 32-bit memory logical addresses. And for systems which give even larger logical address spaces, like 64-bit or something, they usually nowadays use a combination of maybe multi-level page table and hashed page table. So any questions here? Okay, so that is kind of that completes this chapter, but I need to tell you a few things about the next thing. So basically, yeah, this is a summary. So just if I say that, yeah, we first studied contiguous allocation. Then we understood that it is simple, but there are problems like fragmentation and dynamic increase of memory of a process is not possible, or is actually possible, but very impractical. So contiguous allocation with relocation register satisfies some of the requirements, like contiguous memory starting with 0 and so on, but not all. So then we move to paging. We did discuss segmentation a bit, but essentially segmentation has not become so popular. Usually paging has become popular. So paging has several advantages, like avoiding external fragmentation. Also, the process actually sees a contiguous memory starting at 0. So physically the memory is non-contiguous, stored in different frames, but the programmer's view is very simple, that it's a contiguous memory address space starting with 0. So paging has lots of advantages. But then the fourth problem is that, the fourth requirement is that with time, processors require more and more memory. Okay, so the cost is that we have to store the page table in the memory now. The page tables themselves have become quite large. Page tables, because the applications are wanting more and more memory, page tables have become large. And so the page tables have to be stored in the memory. And that means two kinds of issues. One is that multiple memory accesses are needed for each data access. We don't want that. So people have devised schemes like the translation look-aside buffer, TLB, for caching frequently used page entries and so on. Also, another problem is page tables have become huge, and we cannot allocate contiguous memory space for such huge page tables. Therefore, it requires to be thought what would be the structure of the page table. So we discussed like hierarchical multi-level page tables, where the pages so the inner page tables are themselves stored in pages. So we have pages of page tables. But then this scheme does not scale well to really large logical address spaces. Okay. Therefore, we also discussed hashed page tables and inverted page tables. Okay. So, any questions here? I will take 2 more minutes to motivate something else. But any questions here? So again, the slides will be available. Go through them. I know that maybe what we discussed today might be a bit confusing, but go through the slides and also go through the book. The book gives much more explanations than what are there in the slides. So yeah, I mean, there's multi-level page tables. Do understand them. Okay. So let me just conclude with one thought, which will basically motivate the next topic that we will discuss. So we understand that programmers or programs require more and more memory. So they are more complicated programs are being written, much larger data sets are being handled. And so programs are requiring more and more memory. How more? How much more? We talked about 2 to the power 32, 2 to the power 64 logical address space. How much is 2 to the power 64 bytes? Can anyone tell? Say in terms of GB. How much is 2 to the power 64 bytes? How many GBs? Sure, thousands of, no, I mean, okay. So, okay. So basically Deep and Aryan, yes. So 2 to the power 64 is a huge, huge number, right? So like how much is 1 GB? 2 to the power, how much? 30, I guess, or what? Yes. So what? Yes. So 1 GB is 2 to the power 30 bytes, right? So if we say 2 to the power 64, that means huge number of GBs. Okay, so 2 to the power 32 GBs. That's actually thousands of TBs. Okay. Do you see a stray? I mean, does any question come to your mind? We are talking about 2 to the power 64 logical address spaces. Does any question come to your mind? I mean, a question should come to your mind. Exactly what Deep says. You are talking about 2 to the power 64 logical address space. But which machine has that much of RAM? Which machine has 2 to the power 64 bytes of RAM? I don't think any machine in the world has that. Right? Sure, I have seen machines with 1 TB RAM also. But 2 to the power 64 bytes of memory, impossible. So now the thing is, okay, the first three requirements have been satisfied. Also, we now have ways of allowing large memories to processors. But nowadays, processors are wanting more memory than the physical memory size. Right. So that seems like really confusing, but that is the situation now. The programmers are wanting even more memory than the physical memory size. So the idea is this: suppose you have developed a system, you have developed a program on the IIT Kharagpur server, department server, which has, let's say, I don't know, but let's say which has, okay, 1 TB of RAM. Fine, you have developed your program, which requires a huge amount of memory and so on. But now the same program you want to run on your laptop or desktop. Clearly that does not have 1 TB of RAM. Maybe that has 8 GB of RAM, 32 GB of RAM. But if I tell you, no, you need to change your program now, you won't like it. So we as programmers, we have come to demand more memory than what may be even there in the physical memory. Right. So essentially, programs nowadays can want more memory than there is physical memory. Okay, how is that possible? That will be the next topic. The topic is called virtual memory. Right. So any answers? Actually, at the very beginning of this slide set, we had 2 slides on something which I told that we will come back to this later. Anyone remembers? We had this just 2 slides on a topic which, so I said that we are not going to this now, but we will come back to it later because it will play a big role. Anyone remembers? So in relation with this, that how can it be even possible that programs want more memory than is there in the physical RAM? Okay, it's natural to have forgotten. Let me just show you that slide once. So this slide. A process can be swapped temporarily out of memory and then brought back into the memory for continued execution. Right? So, I mean, this will be what will be discussed next. Essentially, using this swap in and swap out mechanism, we can give a process even more memory than what is physically there in our RAM. Okay, because we can think that, okay, sure, a process may have a huge memory space, but it is not that it is using the whole memory space at once. At one point of time, it just needs only a few memory pages, I guess. Maybe those instructions which are being executed now, those data points which are being accessed now. So if we can keep only that much data in the physical space, rest can be in some swapped out state. When it will be needed, we will bring it back. Okay, I'm not trying to explain this thing here, but this will be the next topic, which will be virtual memory. Right? So essentially giving processors even more memory than what is there in physically. Okay. Fine, so I'll stop here today. Any questions? Okay, fine then. So we will continue next week with virtual memory. Thanks everyone.